Shweta ma'am. He joined.
Ma'am, can I start?
Madam Prabhadevi, madam, sir is asking whether he can start, madam.
Sir, can we start the session?
Madam, can I start?
Hello, sir.
Yes, madam. Can I start?
Hello, sir. Sir, can you hear us?
Yes, madam, we can hear you. We can hear you.
Madam, can you be able to view my slide?
Sir,
Yes, sir.
please share your screen,
We
sir.
can able to view your slides, sir. We can able to view your slides.
Yes.
Yes, sir. Yes, sir. Sir, am I audible?
Sir, you are not
Yes,
audible. Could you share? Yeah, your screen is visible, but you are not audible, sir.
Madam.
Madam, sir is audible, madam. Madam, sir is audible.
Madam, whether it is
Hello.
audible?
Sir, for me it is audible, sir.
Sir?
Yes, sir, it is audible, sir.
It is audible. It is audible.
Yes.
Sir, I think there is
Sir,
some
your voice
problem
is
with
not
their
audible.
speakers. Sir, I think there is some
Whether
problem
it
with
is
the
a problem
speakers.
on my speaker?
No, sir. Yours, everything is clear, sir.
Okay.
I think you can start, sir. I will call madam and I'll inform her.
Yeah.
Okay,
So,
okay.
good evening, Munadal.
Good evening, sir. Good evening.
Good evening to all the participants. So, I'm Professor Sivakumaran from Department of Instrumentation Control Engineering, and I am heading the Computer Support Division group of NIT Trichy. I'd like to welcome you all to the AICT sponsored ATAL FDP in coordination with the Department of CSC, Ramaya University of Applied Science, titled Convergence on Quantum Computing and Generative AI for Frontier Scale Revolution, to be conducted from 18th to 23rd of August. So I'd like to welcome you all for this particular interesting workshop. So before I like to, yes.
Sir, we brief introduction. So,
Madam, can you able to hear? Hello?
Sir, we are able to hear, sir, but I think the organizers, Madam Prabhadevi madam and Shweta madam, I think not able to hear you, sir.
Yeah, please
I
check.
think
Please check, madam.
Sir, am I audible?
Yes, you are audible.
Sir, am I audible?
Madam Shweta
Yeah.
madam, you are audible, madam.
Okay.
You're
I
audible, madam.
welcome. Yes, sir. Yes. I welcome
Can you
Dr.
hear
N.
me?
Shivakumaran, sir.
Yes.
Professor in the Department of Instrumentation and Control Engineering, National Institute of Technology, Trichy.
Welcome you, sir.
Yes.
Sir holds a PhD in Process Control and Instrumentation from NIT Trichy and has over 20 decades of academic and research experience in the fields of process control, intelligent system, and biomedical instrumentation. He has published more than 100 research papers in reputed journals and conferences, and has also authored many books reflecting his contribution to the field. He was also awarded an Young Scientist Award by DST in 2007. He has also guided many eminent research scholars and led by government-funded projects from DST, SERV, AICT, and MHRD. We extend a warm welcome to Dr. Shivakumaran and look forward to his insights during this ATAL workshop. With this brief introduction, I now have the privilege of handing over the session to Dr. Shivakumaran to deliver his talk. Sir, the platform is yours.
Yeah, yes, madam. So can you
Yeah,
able to
thank
hear
you.
me?
Yes, sir, yes, sir.
Yes, okay.
Mm. Sir, you're not audible, sir.
Madam, whether can you see able to see my screen?
Yes, sir. Yes, sir. Please put in screen slide share, sir. Slide share mode.
Is that fine?
Yeah.
Yeah. Okay.
Ah.
So whether it is audible?
Yes, sir. Now it is fine. Please
Okay.
proceed, sir. Yeah.
So good evening, one and all. Once again, it's a pleasure to be the part of convergence of quantum computing and generative AI for frontier scale revolution. AICT sponsored ATAL FDP. So in this regard, it's a very interesting and challenging task for me, especially to talk about what is quantum computing and why it is very good realizable for us in NIT Trichy is since I am heading the computer support group of NIT Trichy, you could see that we are 40 years old center, which was established in 1985, and we have inaugurated several buildings, and in 2021 we have the first supercomputer installed at our center, and now it has been well utilized by many of the pioneering structures in other department. So this is a very brief introduction to you, especially with regards to the scale up of how the quantum computing we are going to use for computational intelligence in many of the critical applications of the current scenario. So before we leap into the structure, we need to talk about what is the classical computer, okay, and what is a quantum computer. So this is basically based on the paradigm shift in classical computation, which has a realization of 0 and 1, which is rely on binary system. Quantum machines leverage principles which allow more complex and powerful calculation. So this is a very interesting thing. So far we are discussing about bits of 0 and 1. Whereas in quantum, you could see that the existence of states between 0 to 1, the phenomena is almost like a superposition, which explore multiple possibilities with concurrently leading exponential increase in different specific problems. So this is the first fundamental difference in information processing, which grants quantum computers and their immense potential, enabling them to tackle problems for the ever fastest supercomputers. That is what I have said, that we have installed a supercomputer here in NIT Trichy. And what is the heart of the computing? So any quantum computing is an emergent field in computer science as well as in engineering, which harness the uniqueness of quantum mechanics to solve the problems beyond the ability of even the most powerful classical computer. That is a very interesting phenomena of this. The field of quantum computing includes various disciplines, which is hardware and algorithm. While still in development, quantum technology will soon have a multiple complex problems that uses the classical supercomputer, which can't solve anything with the fast computing. So this is a very interesting thing. And you know very well, basically from the study of physics, very small scale, reveals the surprising fundamental nature. Quantum computers harness the phenomena of assessing the mathematical of solving problems not available in classical computing alone. So this is a very, very important uniqueness which meets the heart of the quantum computing, which is qubits, you know very well, as it is said, based on the superposition and quantum measurements, which talks about the states of zeros and one, which is almost between 0 and 1. So the ability of qubits to exist in superposition is quantum computer to explore the multiple potential solutions to solve the problem in parallel computation. So this is a very interesting phenomena by which it shows the effect of superconducting magnets, how it is going to have the convergence. So what is the key feature, especially in this subject, is it has a superposition of on-off, but entanglement with powerful connections between qubits. It also talks about decoherence. So encoding and decoding of any structure. So that is a very basic principle of an encoder and a decoder in a circuit. So this is how the computation starts.
Sir,
Yes, madam.
sorry to interrupt you, sir. Please put your slide in slideshow mode, sir.
Slideshow only I have put, madam.
No, sir, it is normal slide view only, it is visible.
Oh, 1 minute. Now it's okay, madam.
Still the same, sir. I think you shared your window or entire screen, sir.
Shared my window.
I think you have to share the PowerPoint window, sir. This is a normal slide window is visible.
Okay.
Because the text was small, the audience were not able to see, it seems.
Madam, now it's fine.
No, sir, only your team screen is visible.
Is it okay?
Okay, sir, please proceed because it is not coming. It's okay, please proceed, sir.
Moment.
Now it is fine, sir.
Huh?
Yeah, now it is fine.
Now it is fine.
Again, it went off.
Okay.
Please
Now it's
proceed,
fine,
sir.
madam. Huh?
Yeah.
Okay.
Thank you, sir.
So this is a very interesting phenomena by which superposition and quantum measurements are in existence with the collapse of the structure. So this is how the parallelism in which the quantum computing operates. So in practice, quantum computers are expected to broadly use two types of tasks. One is model behavior of physical system and identify the pattern and structures in information. So it is a bit like operating system of the universe, the computer that uses quantum mechanic principle to process the information has an by and large number of advantage in modeling the physical system. Therefore, a quantum computer of particular interest of chemistry and material science is in place. So quantum computers can also process the data by means of mathematical technique not accessible to classical computers when it is binary and it is of a decoding structure. That means that they can have a structure to data and help the discover pattern of the classical algorithms, which is the application ranging from biology, for example, protein folding to finance. So you see how the example varies from biological things to finance control. So this is what the encoding, entanglement and decoherence of a quantum computer. So when we talk about the key quantum principles, It is not just a fast processing. It is a fundamental quantum mechanics which have no classical counterparts. The principle to emerge calculation is the ways of classical machines that simply cannot. So this is a very interesting entanglement which has to be processed, which is by means of classical mechanics with a simple structure. So why quantum mechanics matters? By Niels Bohr, a pioneer of quantum theory, if you are not completely confused by mechanics, you do not understand it well enough. So this is a very important theoretical understanding of the quantum computers, which are a faster version, but fundamentally there is a directly harness these strange quantum effects with manipulating particles. So under these foundation principle is the key appreciating in revolutionary potential of quantum computing. So this is a very interesting phenomenon. So what can the quantum computers do? Next important thing is, where is the application? So first and foremost, you see drug discovery and material science. For example, superconductors, catalysts, underlying complex chemical reactions, and these applications are with reference to moonshot technologies, and it has a potential to solve the problems on currently deemed impossible, fundamental reshaping industry and scientific discovery. So to understand the quantum computing, it is important to have quantum mechanics principle of superposition, entanglement, decoherence, and interference. So based on these things, the entire operation is going to work. So next is complex system optimization. You work on fine tuning of the quantum optimization, which will leads to algorithm development. And based on that, many of the advanced machine learning, that is quantum machine learning, can enhance the classical AI capabilities. What are all the development with reference to AI model? So what is next? So the groundbreaking next for frontier, which talks about noise intermediate scale quantum, which is NISQ device, and this would help us to configure the data to a centralized processor. So what is the revolution? The revolution begins just like this. So the revolution begins in 1981 by Richard Feynman at MIT with fundamental limits of classical computing, which harness the quantum mechanics, which introduces the concepts of Rubik qubits, quantum bits capable of multiple start contrast with classical power. So classical bits versus quantum bits. So this is a very layman example, like a switch. You see that the foundation of the today's computing is like a switch on-off switch, and the quantum bits, which is a superposition which exists 0, 1, or both simultaneously. This is a very, very fundamental aspect of the coherence in understanding the capability. So quantum phenomena, which talks about the superposition, also has entanglement and quantum tunneling. So when these two coherents are simultaneously felt, what would be the understanding in the system development? So this is what the structure is, which is a scanner in a computer. You could also see how a simple supercomputer, quantum computer, would entangle the effects of these things on the system. So when it talks about the entanglement of the bits and bytes, we need to talk about the different breakthrough in the algorithms. So with reference to these things, you see there is a Shor algorithm, Grover, and quantum Fourier transform. So with this transformation, you could see that the system integrity of making the system at a faster rate is evolved. At a faster rate is evolved. So real world applications in emerging are optimization, drug discovery, and cryptography. So how does it work in optimization, especially in supply chains, financial modeling, similarly drug delivery, especially in revolutionary batteries, optimize the materials for batteries, superconductor, and chemical engineering, cryptography, which is quantum key distribution, which leverage mechanics to create a quantum with secure communication channel. So what are all the challenges in the quantum frontier? So far, whatever I discussed, do you have any doubts? Yes?
No, sir.
Yes? So do you have any doubts?
No, sir. No, sir.
Okay. So with the challenges on quantum computers, you could see that the challenges with reference to 4 different modes. One is coherence. The coherence which talks about the properties for long enough to perform the complex calculations, scaling up with reference to noisy intermediate scale quantum, error correction through valuable qubits in terms of critical for building the truly reliable quantum mechanics, security, which is very important post quantum cryptography. So when I do talk about security, everybody is very keen, especially about the firewall. So how complex your system is, if your system is so complex, how my security system will ensure that these complexities can be reduced further. So quantum computing ecosystem in 2025. So what is the expectation from different segments of computing with reference to technical giants, startups, major players? They need to develop a novel hardware structure, pushing the boundaries of what it is possible. Cloud access. Cloud-based quantum computing platform are democratizing the access to quantum hardware globally, allowing the researchers and developers to experiment without owning the expensive machines. R&D. Vast amounts of public-private funding are pouring in quantum, the drive of error correction techniques, especially in robust quantum system. Education framework are high up with the very task force from physicists to quantum software engineers. What makes it as a revolutionary? This is a very important challenge which we need to come up. So when it comes to qubits, leveraging superposition and entanglement, enabling multidimensional processing. So unlike classical bits, multiple states of simultaneously exponential increasing in computing power enables a complex solution for a massive database. Current quantum computing landscape industry leaders and milestone. IBM is the strong user, Google, Amazon, and Microsoft Azure. So transforming this to an artificial intelligence. So in terms of drug discovery and chemistry. So everybody talks about financial modeling and cyber security. So this is one of the 2 important key structures in data management, especially in India. When it comes to financial modeling, optimize large-scale portfolios, reduce risk by modeling complex market, simulate market behavior with reference to classical system. Cyber security, quantum cryptography promises, because strong encoding decoding is a must for a quantum key distribution. Emerging quantum safe encryption methods to protect data against future quantum attacks. So these are all the important scenarios which is very much looked upon, especially from the process and computing environment. So optimizing logistics, yes, manufacturing, energy in terms of advances in battery materials, semiconductors, and simulation. So what are all the challenges? We have very strong observations, engineering hurdles, data loading, error corrections, and fundamental constraints. So based on this, who is leading the quantum race? So this is very, very important. Even though IBM, Google, Amazon, Microsoft come into existence, many of the government initiatives, startups in India is emerging, innovative startups, and silicon qubits are also emerging like anything. So a collaborative competitive initiative with a promising future in quantum mechanics is very much initiated. So what is quantum technology? So nowadays everybody talks about technology which is also based on the fundamentals of quantum mechanics, which goes beyond the classical technologies and how the principles work together. To better understand the quantum computer, consider the two surprising ideas are both true. The first is that the object that can be measured as having a definite states, qubits in superposition with defined probability amplitude, behave randomly. The second is the distant objects, in this case entangled qubits, can still behave in the ways that, though individually random, are strongly correlated. A computation on a quantum computer works by preparing a superposition of computational states, a quantum circuit prepared by the user, uses operation to entangle quantum bits, which is governed by set of ultra fast computing with a secure communication and precise sensing. So what is a qubit? A quantum concept. A qubit can be a 0 and 1 at same time, superposition, entanglement, shared state even when far apart, tunneling, particles pass through barriers, interference helps in quantum algorithms. So this is a very important thing for inside the quantum look of a computing in by Manin and Feynman in 80s and 81 proposed the independent concept of a quantum computer sources from a IBM. So welcome to the dream. You see the same with Google, Intel, Dewey, Rigid. You see that the operating temperature is very hot, which is minus 273 degrees Celsius. So then what is quantum computing? So use of qubits instead of bits, which performs complex computation faster, which is applied in cryptography, AI, drug discovery, optimization. So superposition and entanglement state. So this is a very, very important equation to talk about what is superposition, what is entanglement, and how it has a coherence, and how it has a. So here the superposition, a qubit itself is a very useful thing, but it can place the quantum information when it holds the state of superposition, which represents the possible configuration of the qubits. Group of qubits in superposition can create complex multidimensional computation spaces. Complex problems can be represented in different phases. So what is the physics concept? So the basic quantum bit, which is an electron, which is in the magnetic field, where a nuclei of atoms exhibit a same property, can it spin with zeros and one? This representation of 1 and 0 using electron spin is a qubit. So superposition can also be in the state of both 0 and 1 simultaneously. Measurement of superposed qubit destroys the superposition of 1 or 0. Operation can qubit that destroy the thing. So this is a very, very interesting phenomena, passing a photon through a half-silvered mirror, which is a superposition principle. So we have detectors 1 and 2. Passing a photon through a half-silvered mirror image. So this is what it is very important for everyone to understand. So why to consider this computing for all? That is very, very important. The development of this classical computer is still in enormous progress. Moreover, the design of supercomputer quantum computers seems to be questionable, almost sure enormously expensive. However, there are at least 4 very good reasons. So quantum computing is a challenge and it is a potential, and computing means it's a must and actually our destiny. So this is very, very important. Can computers, quantum computers, do what classical ones cannot? The answer depends on the point of view. So my question to the audience is, can quantum computers do what classical ones cannot? Anybody? Yes, anybody? What is the expectation of the computation fraternity about supercomputer or a quantum computer? Yes, anyone from the audience? Yes.
You can even post your answers in the chat. If you
Yes.
want to answer, please raise your hand so that I will unmute you.
Yes, what is the expectation? So I have showed a principle of superposition, then you know quantum mechanics, and what is the expectation of quantum computing? Yes, whether or not the computers what we are using will perform quantum computation. Yes or no? Yes or no?
Sir, in case of hello, so in case of classical bits, it can have like 0 or 1 bit at any given time, whereas in case of quantum, we can have along with that 0, 1, we can have a superposition at both the side at the same time, sir.
So when you have a superposition both the time, my question is whether you need a computation to perform in an ordinary classical computer. That is my question.
No, classical computers can't do that. So do we have these quantum computations. Quantum computers.
When the classical computer cannot do such a operation, so what is the expectation of the quantum computers? That is my question. What would be the expectation? So already you have complex mechanical analysis using quantum computers. How it is going to effectively utilize the computation effect? That is my question. Whether your classical bit accept this.
Jaykumar sir, you can answer, please. You can unmute yourself.
Sir, I think automation is simultaneously taken in quantum computing, but we can't proceed with respect to traditional computation method.
Okay. So, but why we cannot proceed is a very, very important question we have to think. Is that right?
Yes, sir. Yes, sir.
So you could see the same superposition with the principle of interference. You could see that the guiding detector helps in to guide the cell accordingly with reference to quantum interference. So based on this, you see how the superposition is happening in a. So consider a experiment which has, you see that the flow of if you are triggering using a automatic gun shooting a bullet with random distribution to all the direction. So how do you converge this to a superposition problem? So this is the physics experiment which talks about two particles can be prepared in entangled state in performing over the one. Multiple operation can entangle the things, and entangled particles are in large apart. So you see that how does a qubit is operated? 2 power 500 states. Quantum computer could represent larger number of atoms is known to be universe for a classical computer. So searching algorithms are developed by Grover in 1996. Grover algorithms takes the operation with the average performance. So when it comes to Grover, you could see that the searching operations are all possible with reference to Grover's algorithm. Choose a qubit, match with each other, change the sign, perform inversion about average, and repeat for 4, measure the quantum state. So this is what the ion trap, quantum dots, transmel, and more in future. So you see that the technology is coming out with different version of the companies. So when it comes to this, the processor environment is said to have a cooled state. It's shielded with 5000 X of data with a vibration phenomena. You see that how the processor is seen for different range of the process environment. So you could see that the D-wave container, Faraday cage for no RF interference. You could see that the RF cage with the system shielding mechanism. So this shield preserves the quantum calculation. So you could see that how the quantum shields are made, how interfaces are established. So it has simulators. See, you can go to these sites for simulators. We have periodic number of simulators. You can work on quantum simulator, adiabatic quantum simulator computer, topological effects, and other universal quantum computers. So what is a adiabatic condition? So when the combination has a Hamiltonian do's evolve slowly. So how the adiabatic quantum computers are evolved? You see that initial Hamilton and problem Hamilton. So this is a real-time example of what I have taken from a D-wave adiabatic computer. You could see that the preprocessor did find the congestion, find the alternatives, minimization model, and redistribute costs. So one is optimized, another is unoptimized. So this is how the problem formulation can be solved by a classical mechanics for a traffic flow optimization using a quantum annealer. So Zandu continuous, which is also one of the building a supercomputer on a single chip, a language strawberry fields, cloud service, or search engines. So European quantum flagship with reference to basic science, communication, computation, simulation, sensing metrology with engineering standards. So based on this, the network of data is stored in the cloud. So the network of data is stored in the cloud, where this particular example shows how the effects are seen. So I'll be citing a classical example. You imagine an automatic gun shooting a bullet. So how does the random distribution to all the direction is evolved? So that is how the experiments will work for quantum random number generator. So you could see that how Google quantum supremacy is evolved based on the cited paper. And you could see how the Google quantum supremacy is evolved in terms of bits in future. It is an extended version of the cryptographic tools. You could see that the cryptography is already in place. How cryptography is going to evolve. So all this is based on the classical experiments, which is on field. So when classical experiments are on field, how does these convergence will work? So quantum experiments are very, very interesting in terms of dealing with numbers. So the best classical algorithm which base for rules is based on the classical quantum computers. So based on this, you see that the cryptographic bits applications are widely seen in many of the digital domain. In case of data storage in 1000-bit digit number, which would require 10 to the power of 25. Yes, so you could see how the bit classifications are evolved. So developed in 1994, the quantum algorithms is supernumerary, and it would have an effect of 1000 digit power factor polynomial time. So new algorithms are cryptographically must be created for quantum computers. It could be used in entangled manner with droppers. So obstacle detections, you could see that the obstacles are also detected in terms of beam effects with different occurrence. And classically example of a bullet, an automatic gun is shooting bullet with a random distribution to all the directions. If you in front of this, there is a wall with 2 holes. So you can see that how the quantum computer hardware is in infancy. So current state of quantum computing research is qubit based on electronic with picoseconds, which is also for nano. And 99 MIT researchers have found 2 qubit quantum computers, and new methodologies are also evolved. So this is a very important question for the audience. Are super or quantum computers realistic? Yes or no? Yes or no? Anybody can answer whether quantum computer is realistic. I am in a meeting. I'll call you. I'm in meeting. I'll call you. I am in meeting, and I'll call you. Yes. Are quantum computers realistic?
Pravita ma'am, you can unmute and answer.
Yes or no? Yes or no?
Yes,
Whether quantum computers are realistic? Yes. Yes or no?
Yes, sir.
So why? So it can be efficiently used for simulation, any realistic model for computation. So there are different examples for quantum computers, of which you could see efficient simulators, phase estimation, factorizing and discrete logarithms, hidden subgroup problems. So how do we, next important thing, so far do you have any doubts? If you have any doubts, I am ready to answer your queries. Any doubts so far?
Sir, there are some questions posted in question and answer session, sir.
Huh?
There are some questions posted in QA session.
Okay. So at the end of the lecture, we can ask.
No, sir. You can answer now also. There's someone is asking, how do we understand the state of qubit in both 0 and 1?
How do you understand?
The state of qubit in both 0
I will go
and
through the screen.
Yeah,
It is posted on the screen. Yeah.
Yeah, it is posted in the QA session. QA is there, now you just click that, it is there.
1 minute. Where is this question board posted?
Sir, you just check that QA, it is there.
I could not able to.
Okay, I will post the question in the chat, sir.
What is the question, madam?
How do we understand the state of qubit in both 0 and 1?
Yes. So a very good question. So when how do you understand the qubit in terms of zeros and one? Am I right?
Yes.
So this is very, very important for you to see that how the qubit works. So that itself is a challenging thing. So it is a group of superposition which can have complexities. Complex problems can be represented in new ways in these spaces. When quantum system is measured, it states from a superposition of possibility into a binary, which can be as 0. So when we have this as a 0 state is a very important analysis. In case of encryption, we'll have is 0, and decryption we'll have it as a 1. Can you able to understand, madam? Hello?
Yes, sir.
Yes. So can you able to see the screen?
Yes, sir. Please continue.
Yes. So this is what the doubt. This is some of the participants are asking. So the information is read as 0 and 1, and you can see what all the the key important thing for moving into quantum computers is that security. So information security protocols must be studied as cited RSA, Rabbit, Gamal, Buchman, Williams, and others. So we need to worry of how these states are classified. So quantum information security is important. Like a firewall, you see, the entire security operations depends only on the laws. So what are all the laws? Quantum key establishment, which is available, random number generator, quantum money, quantum signature, quantum secret sharing, and multiple party information. So what is quantum communication? So quantum key distribution ensures the data transfer, which is a fiber-based quantum communication, and which has a useful transmission through air and vacuum. What are all the challenges, which is of atmospheric turbulence in photon pathway, background light and weather conditions, alignment and beam splitting in accuracy, recent achievements. Now you could see that satellite achieved the ground through QAD and NASA. The ground test informations of 100 plus kilometers are in pipeline. So what would be the expectation in future? So that is what everybody expects. Global internet communication via satellite configuration is done, and integration with classical communication is done. Portable quantum communication devices are established. So quantum sensing is becoming powerful, especially in medical industry. Quantum MRI is in place, is going to be in place, which scale up a huge number of data for medical diagnostics and operations, which really going to help the career of many of the individuals in large numbers. By and large, it will have a quantum MRI with atomic clocks, where you could see the diagnosis plays a very important clinical role, and that would aid the doctors for a faster realization. Nowadays, you could see that even though your discharge summary report generations are faster, healthcare industry is going to have such a realistic understanding to make this as a faster operation. Challenges. What are all the challenges? Are delicate, error correction is complex, high cost, limited hardware, require new way of thinking in programming. Future of quantum technology, huge investment by government and companies are required. Breakthrough expected in maybe next 5 to 10 years. Ethical questions, data privacy, military use. A field full of opportunities. Quantum tech is a transformative technology. So, whatever I have shown, I hope you have seen and how it has been implemented. So, can anybody answer what is HPC? Yes. This is a view of our HPC at NIT Trichy. What is HPC?
High performance computing.
So, what specifically it is used for?
This is used for when we are doing the multiprocessor. At the time, we are the high performance we need into the computing power. So at the time, we are using in this HPC.
Okay, how do you correlate this with the quantum computing?
So when we having the, how can I say, the multi processor, it's going through into the system. So at the time, the vast number of data, maybe it will be processing. At the time, we can go into this kind of technology.
Oh, you see, the specification, whatever you have said is correct. I'm appreciating your effort. It is the specification itself is around 850 teraflops. You can imagine how fast the computation would be. Am I right?
Yeah.
So
yes.
This is one of the best to know that how high performance computing. High performance computing. So this is where the medical industry, space, aeronautics, every space launch vehicle requires such a, it has a complex non-linear data. Am I right? All are non-linear data. How the computation calculation of the complex calculation at a higher speed can be decisive enough. So you could see this is what the configuration of the HPC. It has a series of nodes with connected storage and nodes and normal nodes and GPUs. So GPUs helps to have a faster computation based on the sample. Is that clear? Can you able to understand how this architecture is going to be complex? Am I right? Yes?
Yes, sir. Yes, sir.
So, you see, we have Paramporal 1080 Trichy, which is various supercomputers in India. of which we have Paramporal in Trichy. So it is a state of supercomputer developed under national mission of 838 teraflops, and supercomputer which is operating per seconds in the units of megaflops, gigaflops, and teraflops. So this is how the GPUs of logical computation node. You could see that how the firewall, login nodes, computation nodes with secondary communication, server management, master, primary, and storage. So you could see that how a infinite band of different nodes, different GBBS is going to establish the firewall and service management through a secondary communication. So this is our complex. You see how the how communication data management is done. We have a very strong infrastructure of connecting all the labs with our infrastructure. And this is a brief introduction of what we support. And we also extend this visit for school students. They are always here. We are showing how best the students can involve in this research. So this is the specification of our GPU. You see that your entire it is 838 teraflops with memory and CPU only with computation nodes, GPU nodes, and high memory compute nodes. So this is the software stack of our GPU, of our supercomputer, with the performance monitoring, visualizing tools or different tool sets and application library, with development tools, communication library, cluster monitoring, resource monitoring with the drivers and operating system. And you could see that the same we are trying to use for automation also. For process management, you see that we have distributed network. We
First year, it's not audible.
Participants, sir will join in another 5 minutes. He's having some issues with this. Can you hear me? He's having some issue. He'll be joining in another 5 minutes.
Can you able to hear me?
Yes, sir. Yes, sir. Please proceed, sir. Share your screen, sir. Yeah.
Screen is visible, madam?
Yes, sir. Share your PPT.
Screen is visible?
Yes, sir.
So this is what brief history of my center at NIT. You see that this was how the data center was operating. And you could see that now we have all our all-in-one systems. The entire operation of services, what we are doing is for NIT.
Sir, you're not audible, sir. Sir? Okay. Dear participants, sir is having some issues with the power, it seems. I will post the feedback for the session. Kindly fill in the feedback form. I posted in chat. Please tell whether you are accessible to that.
Hello, ma'am.
Hi.
Hello,
Yes.
Prabha Devi, ma'am. Ma'am,
Yes.
actually, I'm not able to access the chat.
Ma'am, chat is not enabled, ma'am, because some of the mail IDs are unverified. So, if you have any, you can't able to access my WhatsApp. I will post it in the WhatsApp group, ma'am.
In WhatsApp group, I'm able to access. I'm talking
Yeah, I
about
will
the
post it.
Teams.
Yeah, we'll check it out the issues in the tomorrow, ma'am. Yeah.
Okay, ma'am. Thank you.
Okay, thank you.
Hello, ma'am.
Yes, ma'am.
I'm not able to see even Q&A option, ma'am. Neither chat.
Yeah, we're posting in the WhatsApp group, ma'am. Today we can, it is posted there. Please give the feedback there.
Okay.
Tomorrow we'll sort it out. Yeah.
Okay. Thank you.
Thank you. Participants, sir will join in another 5 minutes, and followed by that, 8 o'clock next session will start. Please be online. And this feedback is for the session 1 only.
Excuse me, ma'am.
Yes, ma'am.
And chat and feedback form access is denied.
Yes, ma'am. 2 minutes. Making it.
Okay.
Ma'am, it's so session 2 feedback form. I am audible. Hello. Hello.
Yes, sir.
Madam, access required is access
Yeah, now it is.
permissions required, ma'am.
Yeah, now it is given, sir.
Now it's so session 2.
Yeah, I'm posting 1 minute. Session.
That was a good session from Dr. N. Shivakumaran. Because of some power issues, like we couldn't connect to him. He gave us with the insights to HPC, that is high performance computing, qubit, and quantum mechanics. So thank you, sir. So we now have our next session speaker, Dr. Tyagaraja GS, Professor and Head. And today he will be presenting for a topic of quantum AI. Sir, are you there? Tyagaraja, sir?
Yes, I'm audible.
Can you hear me, sir?
Oh, yes, madam. I'm hearing you. I'm audible now.
Yeah, okay, sir. So Dr. Tyagaraja GS is a professor and head of Department of Computer Science and Engineering at SCM Institute of Technology, Ujjain, with over 21 years of experience in teaching, research, and academic administration. He has made significant contributions to the field of computer science and artificial intelligence. He has authored 3 books and published more than 50 research papers in reputed journal and conference proceedings. He has successfully guided 1 PhD scholar and is currently supervising 3 more under VTU. Dr. Tyagaraja holds a master's degree in physics, a master's in computer science MTech, and a PhD in computer science. His primary research interests include emerging technologies like artificial intelligence, quantum computing, and the theory of mind. Since May 2016, he has served as a reviewer for prominent elsewhere journals such as Applied Soft Computing and Artificial Intelligence. His current research focuses on AI for a peaceful mind. He is also an experienced speaker and resource person, delivering workshops and technical sessions on cutting-edge topics including artificial intelligence, data science, machine learning, context-aware computing, and quantum computing. We welcome you, sir, and it's over to you, sir.
Thank you, madam. Thank you, Dr. Shweta Giri, madam, and also all authorities who have given opportunity for me to share my knowledge in quantum artificial intelligence. Currently, there is a demand of a new type of hybrid technology, which has got more potential in terms of hardware as well as in terms of solving the task very quickly or very fast. In that direction, probably the quantum AI is only the such hybrid technology which can solve most complex problem in a very quick time, or fastly it can solve the things. Okay. In this session, I'm going to discuss about foundations of quantum mechanics and computing. Initially, I will just introduce what is quantum artificial intelligence, how it is different from the artificial intelligence, what is the contribution of the quantum computing and artificial intelligence to each other. Here, quantum artificial intelligence, actually it combines 2 technologies. One is like quantum computing and another one is artificial intelligence. The purpose is to create a new algorithms, to design a new models and develop some systems that can potentially outperform the currently classical AI or purely classical computing exists. Okay, this field aims to tackle high dimensional and complex problems that are currently infeasible for classical computers. Now, you can see that here we have got 2 technologies. One is artificial intelligence, but it has got an immense strength, like it can learn patterns from the data and
Sir, you're not audible.
Okay, here computationally intensive on classical. And this is the main drawback of the existing artificial intelligence. When you come across quantum computing, it also facing some limitations. But its strength is like it can explore multiple solutions simultaneously because of its principles, behavior of the quantum particles. Multiple solutions can be solved simultaneously, but at the same time, it has got limited algorithms, fragile qubits. You can observe here, artificial intelligence can contribute to the quantum computing. At the same time, quantum computing can contribute to the artificial intelligence. That is, artificial intelligence can help the quantum computing in designing a very efficient algorithms, okay, to make use of the qubits effectively. Similarly, quantum computing can provide the multiple solutions for artificial intelligence, where currently the classical hardware is not providing that. Okay, because artificial intelligence day by day it is becoming more powerful and it is exploring the different types of insights and extracting the inferences. Okay, but it is kept becoming more capable in solving the high dimensional and complex problems. But at the same time, hardware is not supporting for it. In that direction, it is the quantum computing that can help the artificial intelligence to show its full potential. Top reasons why quantum artificial intelligence is needed is one is optimization, like providing the best technique or best algorithms, best methodology. Okay, in that direction, quantum artificial intelligence will be very effective in selecting the best like decisions or strategies. It may be any area. It may be like drug discovery. It may be building a house. Okay, it will optimize the thing very quickly, which wherein that current artificial intelligence is not possible. And learning, machine learning, particularly machine learning or deep learning, whatever we are using right now, deep learning, they are not very fast. They are very slow because of the infrastructure that is available right now. But it can be accelerated with the help of quantum artificial intelligence. The deep neural network or deep learning becomes very fast, and inference also will become very quickly. And the high dimensional data, the data currently existing is very low dimensional. Classical computers or classical mechanic principles cannot be applied for high dimensional data. In that direction, quantum computing will become a very top reason why it is needed. The models, particularly natural intelligence, if we go for natural intelligence, by nature, human being is a probabilistic in nature. We are developing artificial intelligence to think and work like a human being. In that direction, classical model once again fails because it is deterministic in nature. It is a quantum artificial intelligence is one which can design and develop a probabilistic models. Next generation artificial intelligence, particularly right now we are here talking about generative artificial intelligence, similarly agentic artificial intelligence. Now in future, there will be a new type of artificial intelligence like quantum generative artificial intelligence, similarly quantum agentic artificial intelligence or quantum agents. Okay, and quantum computing, when we use quantum artificial intelligence, it will become almost near to the human being. And whatever we are talking like general artificial intelligence. Right now we have got like narrow artificial intelligence, which is one specific areas and specific limitations. With limitations, this artificial intelligence is being developed nowadays, and we call it as narrow artificial intelligence. And we have got another two types of artificial intelligence like general artificial intelligence as well as super artificial intelligence. General artificial intelligence is one which is almost near to the human being, which has got all capabilities of the human being, including emotions or non-emotion capabilities, which is right now not possible with the classical artificial intelligence. Quantum artificial intelligence in future, it can be used for unsolvable problems or untrainable problems and understanding the unexplainable things. One thing we have to know that any technology, any new technology, when it comes, it can solve the current limitations or current problems existing based on the current technology. But we cannot confirm that quantum artificial intelligence will solve the all type of problems. But all type of problem that can be solved by classical artificial intelligence can be solved by quantum artificial intelligence with more efficiency, with more accuracy. Okay, in that direction, quantum artificial intelligence is needed. That is the top reasons for quantum artificial intelligence. And also, it may generate new type of problem also. In that, when it generate new type of problems, new technology will come into existence. Now, as already told, quantum artificial intelligence has got a two direction. It is not a unidirectional technology. One is like quantum computing for artificial intelligence, and another is artificial intelligence for quantum computing. Here both are needed. Actually, artificial intelligence is useful for quantum computing also. Yeah, quantum computing is also useful for artificial intelligence. If we take like quantum computing for artificial intelligence, using quantum computers, we can improve the AI algorithms. Quantum computers can process certain types of problems very quickly with a very, very small amount of memory, which is not possible with the classical quantum machine learning. Okay, whether it quantum machine learning or quantum deep learning, faster training of large scale models using quantum computer vision in large scale. In that cases, classical computers face accelerated image recognition faster
Sir? Tyagaraja, sir? Yeah, he's sharing his screen.
Because of rain, it is.
Sir, you're not audible, sir. You're not.
Okay, madam.
Yes, sir.
Am I audible now?
Yes, sir. Fine, sir.
Okay, madam. Thank you. Here heavy rainfall is there. Sometimes network issues are arising.
Sure, sir. Okay, sir. Fine, sir.
I was just talking about how the quantum computing for is useful for artificial intelligence. particularly like machine learning, to make the things learn very fastly, faster training of large scale models is possible using quantum computing. Similarly, I was talking about quantum natural language processing, QNLP. Okay, wherein the natural language processing, making use of the quantum states, becomes more faster semantic reasoning. Similarly, planning and scheduling. Okay, in planning and scheduling, optimizing complex logistic airline scheduling like smart grids is possible using quantum analysis. So these are some of the few reasons why quantum computing is essential for artificial intelligence, to show the complete potential of the artificial intelligence in solving the more complex problems like machine learning, computer vision, or natural language processing, and even planning and scheduling. And artificial intelligence for quantum computing. Using AI techniques, it is possible to make computers work better. Quantum computers are very sensitive to the noise. Even if small noise is there, they will get a collapse, and uh, immediately it will start to behave like a classical computers. Therefore, in order to make them more efficient, artificial intelligence can help in calibration, error correction, and algorithm optimization. For example, machine learning can be utilized for error corrections. Similarly, reinforcement learning can be used for experiment design, like particularly for like artificial intelligent agents. If are discovering themselves the better quantum algorithms or optical setups. A neural network for circuit optimization. We know we right now we are using generative artificial intelligence for like generating the images, generating the new type of contents. Similarly, with the help of the quantum computer, artificial intelligence, that is generative artificial intelligence, can be used to generate the new type of quantum circuits. Okay, which is very hard with respect to the uh, designing the quantum computing circuits using classical computers. And in that sense, artificial intelligence will be useful for quantum circuit design so that it can fit the hardware constraints like this. Generative AI for quantum algorithm discovery, particularly like large language models or code generation models, creating and refining quantum algorithms, like parameterized circuits or problem mappings. Okay, these are all certain examples of where generative AI can be uh, used for quantum computing. Similarly, agentic AI for autonomous quantum system management, particularly when we go for like from multi-agent to the single agent to the multi-agent AI system, monitoring quantum hardware autonomously, calibrating the qubits, scheduling computation workloads, and adapting to changing noise profiles without human intervention is possible with the help of artificial intelligence, particularly the agentic artificial intelligence. Now, the current trends or future trends in artificial intelligence is first of all like quantum enhanced AI tools and platform. That is, there is a need of a new type of AI tools which makes use of the quantum infrastructures, new types of AI algorithms, new types of AI platforms. This is one area where we can do research or we can develop some products. Similarly, generative artificial intelligence. We have right now about generative artificial intelligence, which is purely based on classical things. It can do even better. There is a lot of limitations with the current generative data. In that case, we can make use of the quantum computing and improve the quality of the images or quality of the data that is generated by this generative artificial intelligence. Then quantum AI agents. AI agent is a right nowadays there is a with the very minimum human intervention, but we can make even more powerful AI agent less battery usage. In that cases, we can make use of the
So your screen is not visible. Tyagaraja sir?
I'm rejoining now.
Yes, yes, sir.
Yes, I was discussing about different trends in quantum artificial intelligence, developing a new types of AI tools and platforms, quantum generative artificial intelligence, quantum AI agents, then quantum softwares, new types of software will come, new types of operating system will come, and a self-learning quantum artificial intelligence, which is self-aware or self-healing quantum artificial intelligence, hybrid architectures, which makes use of both like classical artificial intelligence as well as quantum artificial intelligence. And quantum security can more powerful as compared to the like classical security. It can break all the classical cryptography or classical securities and scaling the hardwares. Okay, there will be immense rise in the power of the classical hardware. These are some trends means in the research that we can do in different areas related to quantum artificial intelligence. All these are not actually current trend. They are the future trend or the future work wherein we can do some research work, even like quantum powered electric vehicle design. Right now, electrical vehicle design is based on even the very minimal use of artificial intelligence is there right now. They have to explore, use the full potential of the artificial intelligence. Then they can go for quantum powered electric vehicle design. It will increase the mileage also, and the usage of the quantum electric battery will be very efficient as compared to the current existing battery. Okay, these are some of the trends in and also quantum operating system. Recently, there was a talk on that some company organization has designed like quantum soft operating system. Like that, we can think about different types of softwares, which makes use of the quantum architecture. That is about like what is artificial intelligence, the combination of the quantum computing and artificial intelligence, where it can be used, and what are the future trends or future research work then we can. And foundations of quantum mechanics and quantum computing. Before going to the advanced concept of the quantum computing or quantum artificial intelligence, it is essential to understand some very basics of the quantum mechanics and quantum computing. Okay, I will start with from a very basic concept so that we can understand the advanced concept here. What is quantum? Quantum, everybody aware that quantum means like quantity. Okay, it is quantum means quantity. It originated from the Latin word for how much. Okay, but here quantum refers to the smallest possible discrete unit of any physical property, usually related to the energy and matter. Like energy particles are matters, smallest energy particles, we usually call them as a quantum particles. Example, a quantum of light is a photon. Similarly, a quantum of electricity is an electron. They are the very minute particle, and they are the smallest possible discrete unit. In the light, the smallest unit is photon. Similarly, electricity, the smallest unit is electron. Quantum particle, there are the different types of particles here. in the basic physics, we are aware that there are different types of quantum particles like fermions like electrons, protons, neutrons, quarks, neutrinos, etc. Similarly, bosons, four scattering particles like photons, gluons, W and Z bosons. These are all some examples. Similarly, composite particles like mesons and baryons. Okay, these are some of the quantum particles. Okay, it is not a like complete list of the quantum particle. I just highlighted some of the particles. All the particles is not yet used for like quantum computers, particularly like electron is being used, photons are being used, and ions are also being used. Charged particles are also being used to develop the like quantum infrastructure or quantum computers. Now, what is quantum computing? Quantum, it is a type of computing that makes use of the principles of the quantum mechanics to process the information. Particularly, if you go for classical computer, it makes use of the classical mechanics to process the informations. Therefore, from this definition, it is clear that we have to rewrite all types of algorithms, or even like writing a circuits or designing a circuits. Different types of circuits will come into existence while designing the quantum computers or quantum related objects. Quantum mechanics means what? It is a theory that describes the microscopic particles like photons, electrons, atoms, molecules, etc. All these quantum phenomenon is natural. Naturally, certain behavior of the particles exist. Okay, that behavior has been identified as a quantum behavior. Particularly, these are the five important. There are other principles of quantum mechanics or quantum computing also is there. I've just list here five very important principles of the quantum mechanics. First one is like a superposition and qubits. Second, like entanglement, superposition and qubits. Okay, that is qubit depends on the superposition principle. Then entanglement, sharing the informations. Now to communication, for communication from one qubit to another qubit, this principle is used. For amplification, like quantum interference is used. For decoherence, the avoiding the noise or eliminating the noise, this decoherence is used. And measurement and collapse is very important. Even though the end, when we start to measure, right, quantum phenomenon will get collapses into a classical phenomenon. That means uh, as per the current technology or current understanding of the quantum mechanics, initially classical behavior will be transformed into quantum behavior. And at the time of measurement, once again, it will go back to the classical behavior. Okay. Now let us take one by one here. Superposition. What is superposition? A quantum system can exist in multiple states at the same time until it is measured. Once it is measured, once again, it will become like a classical one. Okay. Until that, during the processing, at the time of processing, it will be a quantum. At the time of measurement, it will become a classical. Example is Schrodinger's cat thought experiment. The cat in this experiment, we cannot say that whether it is alive or dead until it is observed. Okay, until it is observed. This is an example of superposition. For example, this is an experimental setup. Here you can see that there is a radioactive atom, and we know that the radioactive element will decay randomly. Okay, randomly in the sense we cannot predict probabilistically. It is a probabilistic in nature, the decay of the radioactive atom. It can decay next second itself, or it may take like 1,000 years, 5,000 years. At any point of time, it can decay. But at what time it will decay, we don't know. Okay, that is probabilistic in nature. When the radioactive element decays, it will give a signal to this detector. Okay, that detector will notify that the radioactive element has been decayed, and as a result, it will give a signal to a hammer to break this poison bottle. or there will be a loose connection will be there. Immediately, as a result, hammer will hit the poison bottle and the bottle will break and poison will come out. As a result, cat will die. But this will happen only if radioactive atom decays. If the atom does not decay, nothing happens. Cat lives. Okay, as already told, this radioactive atom will decay probabilistically. It may now only it can decay, or in terms of 1,000 years also it can decay depending upon the half-life of that radioactive element. Okay, but before opening the box, the atom is in a superposition. That is, we don't know that is radioactive element is decayed or not decayed. It is natural process. At any time it can decay, or it may take long time to decay. As a result, I can represent this as a both decayed as well as not decayed, and it is a 50% chance. That is 1 by square root of modulus of decayed plus not decayed. This makes the cat state also superb because cat life is depending on the decayed, whether the radioactive is decayed or not decayed. Therefore, even life of the cat, I can express it as a superposition of alive and dead. Either it is alive or dead. Okay, this is the actual experiment that is a basis for the superposition. Now, second important property is entanglement. Two or more quantum particles can link so that state of one instant affect the state of the other. Okay, that is two or more quantum particles can be linked. Suppose if there is a changes in one quantum particle, it is also affected in the other particle, and no matter how far apart they are, distance is no matter. It may be in terms of light years also. If two entangled photons are created with opposite spins, okay, here one thing we have to remember that entangled photons means what? Actually, a single photon will be divided into two photons. We cannot create a two separate photon, bring it together and entangle it. A single photon will be taken and it will be broken into two photons with opposite spins. Okay, only opposite spin photon can stay together. Okay, measuring one spin as up and another spin as down. And when you move one photon with up spin and another photon with another direction spin, that is down spin, they are called like entangled photon. Actually, it is just like the same photon is present in the two places. Whenever there is a changes in the one photon, it is reflected in the other photon also. Okay, for example, this is a two-person here. Person one has got one photon or some one object, entangled object, and she is somewhere far away. It may be in terms of 1,000 kilometers or light years. She sees that that object is yellow. Then the other person who have got other part of that quantum particle is also will be yellow. Then there is no need to transmit this data here. Okay, because this data yellow means here also yellow will be there. Without any signals or any communication cable, it is possible to understand what is there in this object at different places. And if suppose this object becomes quantum object becomes like red, even other object will also become red. That means you can treat this object as an information. So whenever the information changes here, I will type something on the word that is also typed here. Okay, therefore, it is also reflected there. The object remains connected even over vast distance. Okay, this process we call it as entangled. It will be helpful for communication. Another one is quantum interference. Quantum states can be combined. Quantum states can be combined here. When we combine, we call it as a constructive interference. When we cancel each other, we call it as destructive interference. These are all like natural phenomena. Any quantum states, it can be combined. It is naturally combined. Cancel naturally can be cancelled. But at what time they can be combined? You can observe that there is a similarities between the two. Okay, this signal and this signals almost looks same with the common phase angle. There is no phase differences here. Okay, as a result, then when you combine, they don't get cancelled here. It will become more strength waves. Similarly, another set of quantum states here. This is one stage. You can observe that there is a phase difference. Phase difference is there. They are not like a parallel to each other. Therefore, when you combine this, exactly they will get cancelled and you will get a output signal like this. Okay, these are helpful to amplify the current correct solution. Whenever the solution is correct, it can be amplified. Whenever the solution is wrong, it suppresses wrong ones. Another one is important principle is decoherence. Here, qubits lose their quantum properties. This is very important. This is the most challenging task that current quantum computers are facing here. This decoherence principle, that quantum bits loses their quantum properties, okay, due to interaction with the environment, causing loss of superposition and entanglement. That means suddenly it also vanishes, superposition also vanishes, and we cannot achieve the entanglement also because of this decoherence. That means whenever anything is observed, when quantum particles are observed, it loses its quantum behavior. This you can observe, you can see that this one cat is alive and dead. But due to the quantum decoherence, either it will be dead or it will be alive. Any one possibility, not both. Until observation is done, it will be like until before any noise is there or before decoherence is there, it will be in the superposition state. Now measurement state 0 or 1, and the original quantum state is destroyed here. Okay, this is very important. How to measure? Whenever we start to measure, finally quantum bit becomes classical bit here. That means quantum state has collapsed. For example, this is the quantum bit which has got both a component of 0 and component of 1. Once it is, that is a 0 probability is like √3/2, and 1 probability is equal to 1/2. Probability of getting 0 is like 75%. Probability of getting 1 is 25%. That means when it is measured, either we will get like 75% of 0, 25% of 1. Whichever the highest probability is there, that will be considered as the final state of the quantum answers. Now that is about like basic principle. Now if you take a quantum computer, what are the different components of the quantum computer? Okay, quantum computer is a device that exploits whatever the principle that I told you, exploits quantum mechanical phenomena such as superposition and entanglement. These two things are very, very important here to perform any computations here. In this, let us once again understand what is qubits, and then I will move toward the other concepts. Qubit is the basic unit of quantum information. It is like the bit in classical computing, but there is a quantum twist. Quantum twist in classical bit, we can either have 0 or 1, not both simultaneously. But here it is possible to have both 0. We can have a 0 bit also, 1 also, and 0 and 1 also. 0 and 1 is represented by like alpha into ket 0 plus beta into ket 1. Alpha is the amplitude or probability of existence of ket 0, and beta is the probability of 1. And we must remember that alpha square plus beta square should always be equal to 1. This is also a natural phenomenon. Whenever the two states are in a quantum state, they show the behavior like model of alpha square plus modulus of beta square equal to 1. Now, I will. What is the difference between classical bits and quantum bits? We can understand with this. Okay, for example, 2 to the power of 1 is equal to 2. That is, there is a 1 qubit is there. 1 qubit. 1 qubit means number of state possible is 2. That is, one is ket 0 and get 1. Okay, a single qubit can be used as a highly sensitive quantum sensor to measure magnetic fields, electric fields, temperature, pressure. This type of applications you can do with the help of single qubit. If the number of qubit is 2, then number of states possible is 2 to the power of 2 equal to 4. Like state means here one is get 0, 0, get 0, 1, get 1, 0, and get 1, 1. Okay, and they can be used to create entangled states such as the Bell state, like 1 by square root of 2 into get 0, 0 plus get 1, 1. Similarly, here when you go for 3 qubits, number of states possible is 8. Okay, even classical bits will have similar type of formula, but one main difference is like if suppose 2 classical bits are there, 0 and 1, it can exist either as a 0 or that is or it may be 1, any one, but here it can exist in both the case. That is simultaneously it may be 0 and 1. Similarly, 4 means all the 4 states can exist due to the superposition property in case of quantum computing. Similarly, 8 state. If I take 8 state, all 8 state we can be used for the processing. Particularly processing the things, we can use all the 8 states simultaneously. Okay, for example, a 3 qubit computer is used to simulate the behavior of simple molecule like hydrogen. These are some applications. Similarly, with 4 qubit, okay, 16 states are possible, and this type is used in like Grover's algorithm. Grover's algorithm is one which searches the unsorted database. Very quickly it will search it because all 16 states can be utilized simultaneously. Similarly, as the number of qubit grows, and 8 qubit quantum computer can be used to factor large number using Shor's algorithm. As the qubit goes, the problem that it solves will become more complex, and that means it will become more capable to solve the complex problems also, like complex molecules and materials, new drugs, batteries, creation of like electric batteries and other technologies. Okay, right now, as on 2025, IBM has designed a quantum computer up to like around 1,000 qubits, and it has got a target to develop a quantum computer with 1 million bytes in 2030. Now, if you take a classical 2-bit example, here, as I told, it can have, this is 0, 0, 0, 1, 1, 0, and 1, 1, whose binary values are like 0, 1, 2, and 3. Each bit is either 0 or 1. Here, each state represents a unique combination of the 2 bits corresponding to the different decimal values. But the system can only be in one of these states at a time. That is the major difference in like classical computers and quantum computers. It can be 0, 0 or 0, 1, 1, 0, and 1, 1 at particular time. Only at one time, one state. Okay, another state, another time only. Okay, it cannot be, all state cannot be superposition cannot be possible in case of classical computers. The same thing if you take like a quantum 2 qubit system, the same bits here 0, 0, 0, 1, 1, 0, and 1, 1 simultaneously they can exist. Like this is the state. State is equal to alpha 0, 0. That means this is the probability amplitudes of each state, like 0, 0. Alpha 0, 1 is the amplitude of 0, 1. Alpha 1, 0, like this. Every state will be existing at the time of processing. Only at the time of measuring, any one state will be there. That means we can take the snapshot of the, but not the, like we cannot at the end, finally at the end, all states will not exist. Only any one classical state will exist. And all these are complex number representing the probability amplitudes of each state. Now, how to represent these qubits mathematically? if you take like head and tail of a coin, state vectors can be represented by the either, that is by combining head and tail. This is a vector which contains both head and tail. Similarly here, if you take like head means 1 and tail means 0, the state vectors, the head state, when if the state is head, the state vector is represented like this. Okay, 1 means here head. Okay, similarly, if the coin is in the tail state, state vector is represented. Here 1 means 1 in the second position. If 1 in the second position, it means a tail. Okay, head and tail. This is head. This is tail. Head is 1 means it is 100% head. Tail is 0%. Here head, tail. Okay, here tail is 100%, head is 0%. Okay, this is how to represent the state vector for each quantum state, and there are different notation. We call it as a Dirac notation. It is also known as bracket notation. Okay, here we have got symbol different notations like ket notation. Ket notation is a column vector. Okay, and bra notation is a row vector. Bracket means inner product, dot product. We can compute the dot product. It is a scalar quantity. Finally, we'll get some numbers. That is inner product. Outer product is like matrix. It will give some matrix at the end, and it is represented like this. First one is ket and second one is bra. Here inner product is first one is bra, second one is ket. Okay, these notations are very important here to understand the concept of the quantum state. That means quantum state is represented using these four concept like ket notation, bra notation, bracket notation, ket bra notation. Now let us see here with the examples. Okay, here ket means what? It represents a column vector, a quantum state like this. Okay, this is a alpha, beta. Alpha is one state, alpha is a, beta is another state. Ket psi equal to, I can represent using alpha, beta. This is ket notation, column vector. Suppose I want to convert this column into row vector, then you have to call it as a bra notation. And bra notation is equal to complex conjugate of the ket notation. This is the ket. Alpha star means it is a complex conjugate of alpha. If alpha equal to x plus iy, alpha star is equal to x minus iy. Like this complex conjugate it will become. Similarly, beta star is the complex conjugate of beta, where alpha star and beta stars are the complex conjugates of alpha and beta. This is a like a ket and bra notations. Now, general state of qubit can be represented like this always. That is ket psi here. This is ket psi. Okay, notation is very important. Yeah, this is ket psi means vertical line followed by psi, then greater than symbol. Here, bra notation means first one is like lesser than symbol, psi, then vertical line. Then this is a ket notation equal to alpha into ket 0 plus beta into ket 1. These are all column vectors now, where alpha and beta are complex numbers. These numbers describe the probability amplitudes of the qubit being in the states 0 and 1. Alpha represent that how much amount of probability for alpha 0 existence, state 0 existence. Similarly, beta corresponds to the 1 existence. Okay, and this is like with the following condition: alpha square plus beta square should be always equal to 1. This is a qubit state, general state, and basis vectors. There is a concept called basis vector. Every vector space has a basis. The basis means it is the most simplest set of vectors from which all other states can be made. Okay, for qubit, the basis states are like this. Ket 0 is one basis state, ket 1 is another basis state, and this is the like column vector for ket 0, and this one is the column vector for ket 1. Ket 1, you have to remember that second part is 1. It means that it is 100% 1. There is no 0 component here, and this one is 100% 0, and there is no component of 1. 1 represents the probability or amplitude of ket 0 here. 0 means the qubit is in the 0 state. 1 means the qubit is in the 1 state. Okay, this is like a standard basis states. First one is ket 0, ket 1. Now superposition state means what? Here it is represented by like plus. There are different superposition states. Plus is represented by ket plus is equal to 1 by 2 into ket 0 plus ket 1. This is an equal superposition of ket 0 and 1. That is probability of 0 is 50%. Probability of 1 is also 50%. Anyone can be chosen at the end of the measurement. At the end of the measurement, either 0 state or 1 state, both are having a same probability. Ket minus is equal to like 1 by root 2 into ket 0 minus ket 1. This is another type of superposition with a phase difference. There is a difference in phase here. It is plus. That is, if one is in a positive direction, another one will be in the negative direction. That's why phase difference is minus here. Okay. And measurement in qubit notations. Okay, when you measure a qubit, you collapse its states to either 0 or 1. The probability of measuring 0 is alpha square. Probability of measuring 1 is beta square. Example, this is one example we have got. That is with the amplitude of 1 by root 3 into ket 0 and root 2 by 3 into ket 1. And this square is like 1 by 3. There is a 1 by 3 chance of measuring it as 0. Whether we have to measure it as 0 or measure it as 1, there's a 1 by 3 chance of measuring it as 0, and similarly 2 by 3 chance of measuring it as 1. Then inner product and outer product of the states. Okay, we have taken two qubit states like ket psi and ket phi, like bracket notation here. Psi or phi equal to, it is written like this: alpha star gamma plus beta star delta, where ket psi is equal to alpha into 0, ket 0 plus beta into ket 1. Similarly, ket phi equal to gamma into ket 0 plus delta into ket 1. One is like a column vector and another one is a row vector. When you combine that, you will get the things like this. Inner product or dot product you will get. Okay, alpha, beta, gamma, and delta are the complex number, and alpha star and beta stars are the complex conjugates of alpha, beta. Okay, similarly, ket outer product. Okay, and this outer product is represented like this. That is, one is ket psi means alpha, beta. Similarly, ket phi means bra phi means here gamma star, delta star. When you multiply this, you will get a matrix. Previous case, you will get a scalar, some number. Okay, here you will get a matrix form. This matrix describes how the state ket phi can be transformed to the state ket psi. Inner product, one example you will take here. This suppose this one is 3 by 5 into ket 0 plus 4 by 5 into ket 1. Similarly, in ket notation, I can convert that into a column vector 3 by 5, 4 by 5. The bra for this state would be like, since both are real number, it will be like this 3 by 5 and 4 by 5. There is no complex number here. And let us say we have another qubit state like ket phi, like this 1 by root 2 into ket 0 plus 1 by root 2 into ket 1. In ket notation, okay, once again, just like in the previous case, we can write like this 1 by root 2. These also both are a real component. Okay, the bra for this would be like this 1 by root 2, 1 by root. Now let us calculate the inner product here. That is bracket notation phi psi is equal to 1 by root 2 into 1 by root 2. That is 1 by root 2 is multiplied with 3 by 5 plus 1 by root 2 into 4 by 5. Okay. Then 1 by root 2 into 4 by 5. Then you will get here 3 by 5 root 2 plus 4 by 5 root 2. Finally, you will get some scalar value. This is the inner product. Some numbers you will get. The outer product results in a matrix operator. Okay, you take this example 3 by 5, 4 by 5 into 1 by root 2, 1 by root 2. You will get like once again another matrix. This matrix you will get. This new types of matrix you will get. This is the result of product, outer product and inner product. Now, when do you say that two qubit vectors are perpendicular or parallel to each other? Let us take two qubit vector like phi1 is equal to 1 0 and phi2 equal to 0 1. You do the inner product, that is a dot product. Two qubit vectors are perpendicular provided if the inner product is 0. Inner product is 0, 1 0 0 1. 1 into 0 plus 0 into 1 equal to 0. Therefore, you can say that phi1 and phi2 are perpendicular to each other. Similarly, two parallel qubit vectors. Let us take a different example here. Psi1 equal to 1, 2, psi2 equal to 2 and 4. We can express psi2 as like psi2 equal to 2 into psi1. That's why they are parallel to each other. That means they must one must be like multiple of the another. Okay, therefore, in such cases, we can say that they are parallel to each other, psi1 and psi2, because here psi2 equal to 2 into get psi1 is exactly 2 times of psi1. Therefore, psi1 and psi2 are parallel to each other. It may be even 1 time of psi1, 2 times of psi1. It must be some scalar multiple of the other. Now, magnitude and normalization of the qubit vector. The magnitude or norm, sometimes we call it as a norm of get psi, is calculated as like a square root of a square plus b square. Mod of a square, if psi is equal to ab, then mod of psi equal to, we call it as a norm of that psi called square root of mod a square plus mod b square, where mod a and mod b represent the absolute values of the complex numbers, say a and b. Okay, let us say the qubit vector is like get psi equal to 1 by root 2, 1 by root 2. So then magnitude would be like this, square root of 1 by root 2 whole square plus 1 by root 2 whole square equal to 1. Okay, this is how to measure the qubit vector magnitude or norm. We call it as norm. Now, normalization process. In order to normalize, I want to normalize any qubit vector. In such cases, you have to find the norm first. First, determine the norm here. Normalized is equal to 1 by norm into a into the given column vector. That is a by norm, b by norm. If we take like get psi equal to 3 and 4, then norm is equal to square root of 3 square plus 4 square equal to 5. 5 is the norm. Then you divide each quantity by 5. Like 1 by 5 into 3, 4. Divide 3 by 5, 4 by 5. Finally, you will get 0.6 and 0.8. Okay, but verify, you should verify the normalization also. Okay, if whatever the final normalized value you have got, it has to satisfy this condition. That is, the square root of that normalized squares plus that is 0.6 square plus 0.8 square should be equal to 1. Okay, generally whatever the we have done normalization will be correct. Since the magnitude is 1, the vector is properly normalized. Okay, normalization ensures that the qubit vector has a magnitude of 1, making it consistent with the principle of quantum mechanics. Okay, 3, 4, in this example, 3, 4 was normalized to 0.6 and 0.8. Both are now same because the normalized, this is normalized magnitude is equal to 1. Now, what is the angle? How to find the angle between the two qubit vector using dot product? We have got formula like cos theta equal to like a bracket psi1 psi2 divided by mod of psi1 psi2. This formula we can use and find the angle between the two. Just in case of classical linear vectors, here also we can find the angle between the two states. That is psi1 and psi2 states in the vector notations. If you take an example of two qubit vectors like 1 plus I, 0, 0 and 1. Now, first of all, you calculate the inner product. You will get 0. 1 plus I dot 0 plus 0 dot 1 equal to 0. Then find the magnitude of psi1, that is equal to root 2. Similarly, magnitude of psi2 equal to root 1 equal to 1. Then calculate the cosine formula. You apply the cosine formula and calculate the angle between the two vectors. Now you will get theta equal to cos theta equal to 0. Therefore, theta equal to 90 degree. That is the angle between ket psi 1 and ket psi 2. That is state psi 1 and state quantum state psi 2 is equal to 90 degrees, meaning that they are perpendicular to each other. Then we can express the qubit vectors in a linear combination of the other vector also. Like given two qubit vectors psi 1 and psi 2, a linear combination of this vector expressed as like ket psi is equal to c1 into ket psi 1 plus c2 into ket psi, where c1 and c2 are the complex numbers or scalars. Okay, this one example, like we have taken like 1 and 0, 0 and 1, and it can be I can take another a combination vector ket psi equal to 1 by root 2 into ket psi 1 plus 1 by root 2 into ket psi 2. Finally, I will get the answer like this. Okay, therefore ket psi equal to 1 by root 2, 1 by root 2 is a linear combination of ket psi 1 and psi 2. Superposition, so it told that superposition of any two qubits has to be represented like this only, like ket psi is equal to C1 into ket 0 plus C2 into ket 1, that is equal to C1 C2. And all the like superposition, the values will be normalized just like before, that is modulus of C1 square plus C2 square equal to 1. Now there are different types of superpositions. Like first one is like equal superpositions. In this case, probability of 0 and probability of 1 will be same. That is probability of 0 equal to 1 by root 2 whole square equal to 1 by 2. That is 50% chance of 0, 50% chance of 1. This we call it as equal superposition. Biased towards 0 means the superposition is like have got the more probability of 0. This one example where we feel that it has been biased towards 0, 75% chance for 0, that is 25% chance for like ket 1. Then similarly biased towards 1, if suppose the probability of the ket 1 is more, then in such cases we call it as biased towards 1. 1 by 3 into ket 0 plus 2 root 2 by 3. And the next one is closer to 0. It is not like closer to 0 means once again it is biased to 0, but it is very closer to 0, but still a significant chance of being 1. 80% probability is there for ket 0 and only 20% chance is there for ket 1. Then we call it as very close to 1. That means even though it is not under 100%, but it is near to 100%. Whenever it is near to 100%, we usually use the word like very close to 1. Like 93.75% is probability for ket 1 and 6.25% for ket 0. Okay, and ket 0 and ket 1 are actually orthonormal basis. That is, they are perpendicular to each other. If you find the product here, inner product, you will get a 0. Therefore, ket 0 is one basis state, ket 1 is another basis state, and they are not just basis state, they are the orthonormal basis states. And normalizations. Okay, to check normalization, we calculate the norm of each vector. That is norm of this is like 1. Okay, square root of 0, 0. Similarly, ket 1, we can write like this. Okay, normalization of each vector. For ket 0, we have to write like this. Bracket notation 0 and 0, and you will get 1. Similarly, normalization for 1, you will get 1 only. Both for 0, 0, 0 and 1. Since both the terms is same here, like bracket 0 and ket 0, bracket 1, ket 1. If you do the inner product, you will get things. That is, I'm sorry, if you find the norm of that, you will get 1. Both 0 and 1 are normalized since their norms are equal to 1. Okay, unitary operations. This is one concept we should know that while studying the quantum gates or quantum circuits, Okay, unitary operation in quantum computing is a transformation that evolves the state of a quantum system in a way that preserves the total probability, and this will written mathematically like this: U dagger into U equal to U into U dagger equal to I, where U dagger we call it as a conjugate transpose or Hermitian adjoint matrix, where I is the identity matrix. See, all these are some basic properties that one should know in order to understand the quantum computing and to even for writing a quantum novel algorithms. Okay, and this is very important here. Tensor products. Suppose we have what two vector spaces, say V and W. That tensor product of V and W is a new vector space, okay, which is formed from all possible combinations of V and W. We'll take one example here. Therefore, here tensor product of two vectors psi1 and psi2 is denoted by this symbol here, psi1 tensor product psi2. Okay, psi1 tensor product psi2. It is often written simply as like this: get psi1 into get psi2, or get psi1 psi2. Like this also you can write. But more popular way of writing is this one: get psi1, this symbol into tensor product symbol into get psi2. Example 1, this X is there, X is one matrix, this is a one matrix, and I is another matrix. What is the tensor product of X and I? You can observe that 0 is multiplied to like a entire this one. Similarly, I is also multiplied to entire this one. This also like this. Finally, you will get the things 0 into I. This is I. Okay, 0 into I, 1 into I, 1 into I, entire matrix. Okay, then you have to like 0 into I, 0 multiplied to all, you'll get all are zeros. 1 multiplied to I itself, 1 multiplied to I itself, and 0 multiplied to I, all become 0. Finally, this is a tensor product of X into I. Unmuted. Then example 2. Okay, here you can see that we have what tensor product of like 0, 1, 1, 0, and 1, 0. You can just multiply this with this vector, and then this with the resultant vectors. Finally, you will get the matrices like this. You can observe that there is a changes in the final representation. Okay, 0, 1, tensor product 1, 0, and tensor product of 1, 0 equal to like this. Yeah, physically, experimentally, how entangled qubits are created. Okay, it means entanglement means quantum states of two or more qubits that are correlated strongly, that measuring one immediately influences the state of the other also. But how it is experimentally now created, entangled qubits is created. Okay, this is one method. There are multiple methods is there. This is one of the method, like spontaneous parametric down conversion method. A laser beam hits a non-linear crystal. Okay, one photon splits into two lower energy photons. That is, from the single photon itself, two lower energy photons has been created, like signal plus Hitler, like this. These two photons are entangled into polarization. If one is horizontally polarized and another will be vertical, like this. Okay, one is vertically polarized, another one is horizontal polarized. And it is common in quantum communication and teleportation experiments. Finally, this is the final representation of that, like this, like 1 by root 2 into get H, get V, vertical polarization, horizontal polarization, vertical polarization, and horizontal polarization. Okay, here the main key idea is entangled photons do not send signal to each other. This is very important. They don't share any signals. They share a single quantum state. It is actually the originally single quantum state, but they are separated. When Alice measures her photon, its state collapses. instantly Bob's photon is also forced into correlated state, same collapse state. Okay, this correlation is stronger than any classical relations, but no unable usable signal travels faster than the light. See here, that means the main key idea is single photon is taken from that only to entangled photons is created. Okay, entangled photons are generated and then directed to the fiber optic cables or any free space optics to different locations. Okay, for example, Messier satellite experiment done by China in 2017, the entangled photon pairs were sent about like 1,200 kilometer apart to two ground stations. Okay, now to even then there was a that is communication was there without any signal between the two entangled photons. Okay, each side measures their photon in chosen bases. Measurement outcomes are random, but always correlated. Okay, they are always related to each other, even though they are outcomes. Every time you may not have the same probability or same amplitude. Okay, and at the end, one can even do the classical communications and check what is the whether the quantum sharing has been happened or not. To make sense of the results, Alice and Baum compare nodes over a classical channel just through like radio or internet or fiber or through some mobile phone. They can say that what are the changes in the they are observing in the final quantum states. Only they can verify the entanglement. The entanglement of qubits in Hilbert space, we call this vector space as a Hilbert space, and they cannot be factored here. This is very important. Entanglement involves quantum state. They cannot be factored into separate state of individual qubits. I cannot separate 0, 0 here, 1, 1 here. That's why we call this state as entangled state. Okay, and that Bell state is one specific quantum states of two qubits that are maximally entangled. Okay, there are four different types of Bell states here. One is like 5 plus. 5 plus is equal to 1 by root 2 into get 0, 0 plus 1. These are all entangled states. Okay, the state representation, two qubits that are perfectly correlated. If one qubit is measured in get 0, the other is also be in the get 0. Okay, and similarly for the one state. That means you both are entangled here. Get 0, other is also get 0. First one is get 1, another one is also get 1 state. Here, similar to the previous one, but there is a phase difference. Okay, between get 0, 0 and get 1, 1 components. Another one is if the first bit is 0, then second bit will be 1. If first bit is 1, second bit is 0. This state represent two qubits that are anti-correlated. That means even the anti-correlation is there, there is a common pattern is there. Okay, therefore we can, this is an example for entanglement. If one qubit is measured in get 0, the other will be in the get 1 state and vice versa. Similarly, to like psi minus, it is also similar to the psi plus, but relative phase difference of -1 is there between 0, 1 and 1, 0. Okay, and we can represent these states in complex numbers also, like polar coordinates are complex numbers. For example, z is equal to x plus iy, where I equal to I square equal to -1 or I equal to square root of -1, and in the complex number notation we can represent like this: z equal to mod z into e raised to the power of I phi. This is a block sphere which is used to represent the qubits. Okay, it is a unit sphere where r is equal to 1. Okay, the state of a qubit can be represented as a point on the block sphere. You can observe that this is it looks like a 3D block sphere, and the points on the block sphere actually represent the superposition of ket 0 and ket 1. Okay, it has got like different axes, Z axis. You can take a Z axis here. Z, this one upward Z, it represents the ket 0. And the down one, it is ket 1. Okay. Here alpha and beta are actually complex numbers, and ket psi can also be represented in this notation like cos of theta by 2. Okay, and plus sin theta by 2 into e to the power of I phi into ket 1. Okay, it uses three axes, Z, X, and Y. Z axis represent the probability of being measured as 0 or 1. Okay, similarly, X axis represent the real part of the state vector. Okay, this X axis means here real part. Okay, this Y axis is imaginary part. Okay, Z axis is 0 or 1 notation. Okay, we'll take another example here. Ket 0 equal to 1, 0. Here, with this equation, okay, using this cos theta by 2 into ket 0 plus e to the power I phi into sin theta by 2 into 1. Whenever theta equal to 0, phi can be any value, but typically we can take phi equal to 0. Any value you take does not matter. But when theta equal to 0, this ket psi will become ket 0 and it will be 1 and 0. Okay, this is ket 0. Similarly, we have got ket 1, 0, 1. Here it is angle is theta equal to phi. This one is ket 1. Phi can be any value, but typically we take phi equal to 0. Okay, ket I equal to 1 by root 2 into 1i. Here for this theta equal to pi by 2, you just substitute theta equal to pi by 2, phi is equal to pi by 2. Finally, you will get this answer, that is ket I is equal to, that is psi is equal to I 1 by root 2 into 1i. Okay, similarly, for different substitutions like theta equal to pi by 2 and pi equal to minus pi by 2, we can represent the minus I. Similarly, theta equal to pi by 2 and phi equal to 0, we can represent the plus, ket plus. Okay, now there is some basic mathematical concept that is required to understand the quantum bits. And now quantum register, we got different component of quantum computer. Quantum register is a system comprising multiple qubits. Okay, it is just like analogous to the classical processor register, that is quantum register. Quantum gates is a mathematical operation that acts on the state one or more qubits, and it can be represented by a matrix. There are different quantum gates are there, like poly gates. Under poly gates, we have got like X, Y, Z, X, Y, Z, Hadamard gate, phase gates, controlled gates, swap gate, Toffoli gate, Fredkin or a C-swap gate, identity gate, and rotation gates. Okay, here, poly gate, it is notated like this. The notation that is used is X. We have three versions of the poly gate, like X gate, poly, X gate, and this is a matrix that is used to represent the poly qubit from ket 0 to ket 1, ket 1 to ket 0, and vice versa. That is, this is the effect on qubits. Poly X gate into ket 0. Okay, you just matrix multiplication, this one and this one, if you multiply, you will get like ket 1. Similarly, X into ket 1 equal to ket 0. Poly, this X gate is represented by matrix. Okay, this is the actual representation 0, 1 or 1, 0. It is also equal to this one, ket 0, bra 1 plus ket 1, bra 0. Both are equal here. And this is another example, X into ket 0. X is 0, 1, 1, 0, 1, 0. If you multiply this, finally you will get a ket 1. Now poly Y gate. This is the notation that is used for Okay, poly Y gate. This is the notation that is used. The Y gates flips the qubit state and adds a phase of 180 degree here. It is Y into ket 0. It will become like I into ket 1. Y into ket 1 minus I into ket 0. And this is the matrix that is used for Y gate. Okay. Similarly, Z gate, poly Z gate, it flips the phase of the qubit state 1, leaving 0 unchanged. That is when you applied your Z into ket 0 equal to, you will get ket 0. Similarly, Z into ket 1. That means when you apply Z gate to the ket 0, no changes. Okay, when you apply it for ket 1, it will becomes phase flip. There is a minus ket 1. Hadamard gate is one which actually used for creating a superposition of the states. Okay, the gate, when designing a gate, if you want superposition of the ket 0 and 1, then you have to use a Hadamard representation, that is h equal to 1 by root 2 into 1, 1, 1 minus 1. Similarly, h into ket 0 is equal to this much. H into ket 1 equal to 1 by root 2 into ket 0 minus 1. You can observe that after multiplying h with ket 0, now 0 has entered into a superposition of 0 and 1. When h1 is applied to ket 1, it is also gone to superposition state, but with phase difference as compared to that previous one. Okay, applying the Hadamard gate to 0, it gives an equal superposition, that is 50% chance for 0 and 50% chance of 1. Then we have another gate called S gate, phase gate. S gate is a phase gate that applies phase of 90 degree to the qubit. That is, whenever you apply S to 0, there is no change effect on qubits. S into ket 1 equal to I into ket 1. Now T gate is another phase shift gate, and whenever you want a phase of like pi by 4 degrees, then you can use this matrix T equal to 1 0 0 e to the power I pi by 4. And when you apply that, it has been effect has been observed like this. T into ket 0, finally it will give only 0. T into ket 1, it will give like this. Okay, this already we discussed. Okay, another gate is C0 gate, controlled C0 gate. Okay. C0 gate, a matrix that is used is like this. Okay. And if the control qubit is 0, the target qubit remains unchanged. These are the behavior that is observed whenever you use this C0 gate. It is also known as controlled X gate. Okay, if the control qubit is 0, there are two bits will be there. One is control qubit and another one is target qubit. If suppose out of the two bits, if first one we call as a control qubit and second one we usually call it as target qubit. If the control qubit is 0, the target qubit remains unchanged after applying C0. Okay, and if the control qubit is 1, the target qubit is flipped. For control qubit 1 and target qubit 0, it will become like this. C0 when it applied to 1 and 0, it will become 1 and 1, because this one is first one is like control bit is 1. Since the first one is control is 1 and target bit is 0, then it will do the changes to 1. That is a target qubit is flipped. Flipped in the sense 0 becomes 1. Okay, C0 into 1 0. Finally, we will get a 1 1. Okay, the C0 gate is represented by this 4 cross 4 matrix. Okay, these are the different C0 gate acts on 2 qubits which have 4 possible basis state like ket 0 0, ket 0 1. The minimum requirement is 2 qubits for the application of C0 gate. Similarly, 1 0 1 1. Okay, and 1 0 equal. If you take one example, applying C0 to 1 0, the input state 1 0 corresponds to the vector say 1 0 equal to 0 0 1 0. C0 dot 1 0 equal to, you will get like this. you do the matrix multiplication, finally you will get this one. This is nothing but like quantum state 1, 1. Okay, similarly, we can like control Z. Okay, control Z gate. Okay, you can swap gate. Another gate is like swap gate. It swaps the states of 2 qubits. Okay, the states of 2 qubits are exchanged here. For example, when you apply the swap gate to get 0, 0, it will become 0, 0 only because there is both are 0, 0 here. When you apply swap gate to 0, 1, it will become 1, 0. Okay, similarly, for all the other states like this 1, 0, 1, 1, like this. Similarly, other gates are there. Okay, their behavior changes suitably. We have to use based on the problem that we require. We have to keep on using different types of gates here. Okay, Toffoli gate. Toffoli gate is a 3 qubit gate where 2 qubits acts as a control bits here. 2 qubits are control qubits. Okay, and the third one is the target qubit. The target qubit is flipped if both control qubits are 1. This is the behavior of the Toffoli gate. That is, the target qubit changes provided both the control qubits are 1. Okay, if both qubits are 1, 1 and target qubit is 0, and it will become like this. This is a 8x8 unitary matrix that is used for Toffoli gates. When Toffoli gate is applied to 0, 0, there is no change. 0, 0, 1, no change. 0, 1, 0, no change. 0, 1, 1, no change. 1, 0, 0, no change. 1, 0, 1, no change. Only first 2 control bits should be 1, 1. In both the cases here, control bit is 1, 1. Therefore, 0 has become here 1 and 1 has become 0. Okay, this is the behavior of the Toffoli gate. Then identity gate, it is similar to identity matrix. I into ket 0 remains as ket 0. I into ket 1 equal to 1. Rotation gate is also there, like Rx rotation among x-axis. Okay, similarly rotation among y-axis. Okay, rotation among z-axis. Okay, the single qubit gates are generally shown as squares. These are the notation. These are the single qubits. Poly X gate, Y gate, poly Z, Hadamard gate, Toffoli gate, swap gate, like this. Okay, NOT gate, also known as X gate, are also sometimes denoted by circle around a plus sign. These are the different notation. Swap gate is denoted like this. Okay, this is the notation. While writing a program in Python, you have to remember this while designing any circuits. Okay, controlled gates. Okay, there are different types of controlled gates like controlled NOT gate. Okay, and controlled NOT gates, controlled NOT gate. This one is controlled NOT gate. Similarly, and controlled swap gate, or it's also known as Fredkin gates. The notations, this is plus this one. Controlled swap. This one is controlled NOT gate. This is controlled NOT gate. Okay, these are the set of different gates I just mentioned here. Poly X gate, poly Y gate. These are the matrix one should remember while writing any algorithms. Okay, Hadamard gate, phase gate, Toffoli gate, controlled NOT gate, Z gate, swap gate, and here Toffoli CC NOT, CC X top, like this. Okay, then quantum circuits. Okay, just quantum circuits. It is a combination of quantum gates and are used to perform quantum algorithms. Okay, here algorithms means circuit itself. We call it as an algorithms here. Quantum circuit is a series of gates that act on one or more qubits. Okay, these are the three input gates. Okay, these are the Hadamard gates. Like this, finally we'll get. It's a combination of multiple gates here. All are here. I'm using some Hadamard gate, set of Hadamard gate. Finally, I've got some output here. Designing a quantum circuit itself is like writing an algorithm. First, we have to write an algorithm, and finally, we have to design the appropriate quantum circuit for a given problem. Okay, quantum processing unit, it makes use of both registers and gates. We call it as QRAM. In QPU, it includes QRAM, quantum control unit, just like in case of classical computers. Classical controller interface, which defines the interaction between the CPU and QPU, quantum processing unit. Then measurement devices. Okay, the quantum measurement is all about like obtaining information about the state of a quantum system. As already told, quantum state once measured, it will become finally the classical bit. Quantum state will collapse. Quantum sensors, quantum microscopes, quantum clocks, quantum gravimeters, and gyroscope. These are some of the examples of measurement devices that are used to measure the probability of the amplitude of different states. Okay, while explaining, we have taken only 0 and 1 state, but in real time, we'll have multiple states. Okay, this is the architecture of any quantum computer. Right now, we don't have like complete quantum computer. This is a hybrid of both classical as well as quantum computer. Only the processor part will be the quantum and algorithm part will be the quantum, and remaining is like classical. That means we will give the input to the classical devices only. Here, business applications, high-level language is used to the cloud or network, and we'll writing a programs in quantum programming environment and creating in circuits, algorithms, assembly language like this. And there will be a like classical interface towards the quantum computer. This quantum and classical interface. That is classical input will be mapped into the quantum components here. Then it will go to the processing, quantum processing unit. Then finally, it will be in the terms of like qubits, interconnected circuits or QRAMs. Okay, the very important thing is like a quantum computer needs a cooling system. Okay, that is the operational temperature for most superconducting qubit is like a 10 to 20 millikelvin. It is just about 273.15 degrees Celsius. Okay, these are some quantum computer cooling systems. Okay, like a dilution refrigerator, it makes use of 10 million that is Kelvin, 10 millikelvin. Okay, superconducting qubits. Similarly, adiabatic demagnetization, it has achieved like 2000 millikelvin. Similarly, pulse tube refrigerator, it has achieved 4000 millikelvin. These are some examples like 2-day cooling system, 100 millikelvin, immersion cooling system, like 1 Kelvin. This is very important for quantum computers. This itself is challenging. This is one I think everybody have seen this type of the images in the Google. Okay, here this is the room temperature. Okay, there are so many coaxial cables, and it starts from 300 Kelvin. It passes through different cooling system, and it reaches 40 Kelvin, 4 Kelvin. Finally, it will go to the 1 Kelvin, 100 millikelvin. Okay, then 10 millikelvin. And the chip is here. Actually, the chip will be here. At the bottom, a very small chip will be there. And that is actually a quantum computer. And most of the thing is like a refrigerator only. It is just like refrigerator inside another refrigerator inside another refrigerator. Most of the component is only for cooling system and transmitting the quantum states. And this is the chip actually, it is there in this bottom. This is the chip structure. It will be hardly 1 centimeter in dimensions. This is the another picture of that chip. Okay, I think I will end this session here itself. Okay, thank you for listening the things patiently.
Sir, thank you so much for your detailed session, sir. It was really very integrate and most of the concepts very clearly and deeply covered. Thank you so much, sir. Participants, if you have any doubts, you can unmute your mic and you can ask.
Hello.
Hello.
Yeah, sir.
Yes, sir.
I have one, two queries, sir. Like first of all, suppose we have a lot of mathematical model you explain here and a concept. Sir, I am facing issue how to implement. Suppose we have any data set like suppose we have any function like Gaussian function f of x. We have that e to power minus x square by 2. That's just like simple Gaussian function. And based on this, I'm generating some values, suppose a data set by using this function. So in quantum computing, how we are going to implement these functions, basically, because quantum computing only work on the 0, 1, whatever qubit we are using, 1, 2, whatever, till now we are using 2. So how we are going to implement this function in quantum computing, using any simple model, whatever model we have. Because f of x, we have a data set that very simple. We have each power x square minus x square by 2. That is a Gaussian function I'm taking. And x value we have and generating a data set. That data set we have to use in a quantum process. So how we can use, sir? That is a problem I'm facing by doing my work.
That means you have got some data set that just like a classical computer, you want to use the quantum computer. Is it right?
Yeah, definitely, sir. We have any data set. Suppose we can generate in data set, any kinds of, and that we suppose we want to implement a quantum computing concept. So how we can implement it? Because we have functions already. We explained some functions like psi functions. We have different even psi functions. We have a different angle also like that. Blochers where we explain. Yeah. So in that Bloch space, how we can implement all these functions? Sorry, data.
Say block sphere is there. Actually, block sphere actually tells that the quantum, what is the amount, quantum probabilities, what are the different types of quantum probability that we can represent in the square. Usually sphere is like infinite points it can take, is it not? Okay.
Yeah, definitely.
Infinite points will be there. Then
Yes.
that means so much amount of that is states can be written using quantum computer. That is the theoretical this one. Simulation. We are using a simulation. There is no such hardware, complete hardware. Like I already told, IBM has got capability like 1,000 qubits. Right now, they have designed a quantum computer of 1,000 qubits. We are using even today like classical integrated with the quantum. You can regularly use your laptop only, but you have to make use of quantum computer at the back end. Only processing will happen very quickly. Like IBM Qiskit is there. You can connect your laptop to the Qiskit and give the work just like in your regular work. Machine learning algorithm you can run. But at the back end, it will be working like that. Front end is even today the classical only.
Yes, sir. Actually, suppose I want to do modeling, sir. Suppose I do not want to any simulations like quantum simulation, basic circuit. I want to do model by using the modeling because a lot of mathematical model we have. So it's possible to implement the same thing, whatever data set in the modeling, that mathematical modeling. Can I do like that?
You have to write a circuits. Circuits I showed, no, one example I showed, but there is a different circuit for different algorithms. Like Grover's algorithm is there, Shor's algorithm is there. To run the algorithm, you have to design a circuit.
Okay.
I have shown only simple example that probably the next session sir will tell. That is algorithm running. Okay, that actually you have to design the circuit separately for the different problem. Then you can use all problem that you are using in classical computer can be written in quantum computer. But you have to design a separate different circuits for that.
Yeah. Actually, I'm facing this one, sir. Suppose like we know that Generally, quantum computer learning is based on the quantum mechanics, and quantum mechanics, that basically we are going to study all the property of electrons in the atoms, that how going to be work in the electrons in orbit and different orbit, different orientation based on the energy level. So this is theoretical things that this is not possible to do experimentally for our engineers. That's it's very difficult.
Yes. This is only, you see, this is the basic concept that I told to understand what is the difference between classical computer and quantum computer. And it depends upon the person. When if you are like a software a developer, there is no need to you have to know at least knowledge about that, but your duty will be writing an algorithm only. Once again, just like in a classical computer, we are writing algorithm. No? Similarly, we have to write there only.
Yeah, so I'm facing here issue only. Sir, suppose we have having so many data set. Suppose you want to convert in that matrix. So for that, that is the main how to convert this in this relation. Means area I'm facing challenges, because that very simple way, electrons either energy going to be exist that area, that will probability high, probability density. If not existing, that probability is zero. That is a practical quantum technology saying like that. Means quantum mechanics saying like that. But the mainly problem, how we are going to implement, we have any synthetic data, that what we are saying, that any functions or any real data we have that because that data set we have to convert in 0 form and 1 form. But that is the problem, how we to convert. That is the main challenges, because here I'm stuck always.
Yes. Finally, what actually happens now? Yes, 0 and 1. Final state is 0 and 1. Before the collapse, this whatever the I said it. Once you measure the data, once you measure that circuit values, okay, at the time of measuring, it will collapse just to 0 and 1. At that particular moment of time, whatever the 0 value is there or 1 value will be there, that has to be captured and we have to use it for the further processing. Usually I have taken only 0 and 1 here. Actually, in real time, quantum computer does not have only 2 qubits or 3 qubits. It will be in terms of million qubits will be there, and all qubits will be finally give one state separately. Okay, at the time of measurement. Therefore, that measurement itself is a result for our solution. It will become very fast, and at that time, since it uses a million qubits simultaneously, it will process the things. And for each state out of 0 and 1, whichever has got the highest amplitude, that value will be considered. And finally, we have to integrate and estimate the answers. Actually, collapse is not only a problem here. At that time, it is just like capturing the processing things in the different states, so that we will do at the end. Okay, that even though it will collapses, but since there are million qubits will be there, it will do the task very quickly.
Yes, sir. Yes, sir.
I think you are actually thinking in terms of very zero. That I took very simple example. For whenever understanding purposes, we will take a simple example. But when implementation at the back end, it will be utilizing like more number of qubits simultaneously. As a result, the solutions becomes very fast, and the final value will be calculated based on the highest amplitude states.
Yes, states. And highest amplitude in the sense of energy levels or normal, because that electrons, whatever photons, particles are considered as a wave nature. So that way, we are going to consider that the energy level, I think so.
Yes. Basically, that state means here the change in energy level only.
Yeah.
Okay, basically, at the that's why temperature is maintained.
Highest energy level means that particular angle. Suppose you are getting highest energy, it means we have the probability, highest probability.
Yes.
Yes, sir. Okay, thank you, sir.
Yes.
Sulochana, sir.
Okay, madam.
Can we say it is only the faster than classical computers when we are executing any deep learning algorithm like CNN? So on classical computer, how much time it is taking for training? And then if we replace these classical computers with quantum computers, then it will be only faster processing. Is this
faster and optimized, madam? It is optimized as well as speed and optimization is the two basic thing that happens here, because it hardware is a different from different perspective. We are designing a quantum hardware. Quantum hardware has got like a quantum bits. Therefore, this change is this one only. Whatever the thing that we cannot solve right now, because for example, if you take a deep learning, you told deep learning, certain problem are there. It will take more time to learn the things, but we need learning should be happen within like in terms of 1 second or 2 seconds, or even like 1 day or 2 days. Certain problems are there which has been taken by classical computers in terms of years also. That can be reduced into 1 week. That itself is the major thing that we can go. Even artificial intelligence is also nowadays you can observe the artificial intelligence is also used to solve the problem, all type of problems very quickly.
understanding the classical computers are using 0, 1 bits, and here qubits are there. So is it
Qubits, sir.
Can we say like this?
What, madam? I am not audible.
Faster than the classical computers?
Yes, madam. Yes, faster, very faster than the classical computers. Am I audible?
Yeah, yes, sir. Participants, do you have any other doubts? Anybody?
Hello, sir. This is Dr. S.
Yes.
Chandramurthy. What about the impact of AI in quantum computing? So now we are in the era of AI. So whether the AI supports quantum computing or quantum supports AI in future?
Sir, in future, actually, both are needed, sir. Quantum computing needs artificial intelligence, particularly to reduce the error. As already told, suppose even a small measurement, unknowingly, even some small noise occurs in the environment, it will stop there itself, and superposition and entanglement will collapse. Okay, before getting the end result, there will be a collapse of the superposition, also entanglement. It can be avoided using a proper artificial intelligence algorithm. It can select an algorithm, that means for quantum computers to reduce this noise and improve the accuracy. In that sense, we can use artificial intelligence for the improvement of quantum quantum computing performance also. Using classical algorithms, quantum computing that is algorithms cannot achieve better. Once again, it will be prone to more errors like this. And also there is a need of agentic artificial intelligence also for quantum computing, because the agents are one which will take the decision without any human intervention. Therefore, it can handle all these types of error correctly. In that sense, artificial intelligence is very essential for quantum computer. At the same time, for AI algorithm to run, we need a quantum computer, because nowadays we know that data is growing like anything, and current infrastructure is not at all sufficient. In that way, in order to create agents, in order to create a generative artificial intelligence more with more performance, in that cases we need like quantum computers.
Thank you, sir. Thank you.
ಇವತ್ತು ಮಳೆಗೆಲ್ಲ ಸ್ಕೂಲ್ ರಜಾ ಕೊಟ್ಬಿಟ್ಟಾರಲ್ಲ ಅದಕ್ಕಿಲ್ಲ ಅಂತ ಇವಾಗ ಸಂಜೆ ಬಂದಿರೋದು ಬೆಳಗ್ಗೆ ಅವು ಇದಕ್ಕೋಸ್ಕರ ಶಿವಮೊಗ್ಗ ಯಾವ್ದು ಇದು ಅಂತ ಹೇಳಿದ್ರು.
Disturbance is there from some.
Participants, do you have
Please.
any other doubts? Yes, yes. Can you please unmute yourself? Yeah. Participants, do you have any other doubts? Anybody? So I think someone has asked. Meghna ma'am, you want to speak? Sir? Tyagraj sir? Tyagraj sir, can you hear me?
Yes, I'm hearing.
Yes, sir. Thank you so much for the session, sir. Please do share your PPT, sir.
Okay, madam. Okay, thank you.
Yes, sir. Yeah.
Okay,
Thank you so much, sir.
Okay, madam.
Thank you very much,
Thank
sir.
you, sir.
Okay, sir.
Thank you,
Okay.
sir.
Thank you.
Thank you, participants. We shall see in the tomorrow's session. Thank you so much for your listening.
Thank you, ma'am.
Thank you very much.
Yeah, thank you. Yeah,
Okay,
thank
ma'am.
you.
Thank you.
Thank you, ma'am. ಮುಗೀತ್ ನಮ್ದುವೆ ನಾನು